Welcome. As advertised in a previous video, I wanted to talk about how a transformer is able to step down or step up voltages. Actually, it's not at all magical. Transformers are always trading off. Whenever they step up voltage, they actually are lowering the current. So it's always an interchange between these two. Whenever a transformer steps up the voltage, the cost of that is that the current or the electricity, the flow rate of electricity has to slow. And vice versa. Whenever the voltage is stepped down, that means the current has to increase. I want to show you what that looks like. Okay, earlier on, or in the previous video, we saw that the law of transformer for voltages, the transformer law for voltages can be written this way. However, if we're dealing with a transformer that is 100% efficient, in other words, there are no losses, there's no loss of energy when it's operating, we can safely assume, actually there's no need to assume, we could safely say that the input, the power that we pump in on the primary side must be the power we obtain on the secondary side. Another way of saying that, or mathematically stating that, is that the power input on the primary side, P sub P, power on the primary, is going to be equal to the power on the secondary side. But what is the expression for electrical power? Well, electrical power is given by I, the current, times the voltage. That's what electrical power is defined as. You're welcome to check the units and convince yourself that this is so. So for an efficient transformer, the primary side, the power is going to be the current on the primary side times the voltage on the primary side. The same goes for the secondary side. It's going to be the current on the secondary side times the voltage on the secondary side. But remember, what did the transformer law for voltages teach us? It taught us that the voltage on the secondary side is equals to the turns ratio times the voltage on the primary side. So instead of V sub S, we could just substitute this entire thing. And when we do so, we will obtain this expression. But Vp is common, so we could cancel that out. Look at what this teaches us. This teaches us that the current on the primary side is related to the primary on the secondary side through the turns ratio. Notice, now it's the primary equal to the turns ratio times the secondary. Compare this with the voltages. The voltages, it was the secondary equals to the turns ratio times the primary voltage. What does this mean for us? This means whenever the turns ratio is positive, is larger than 1, that means the current, so whenever we have a, well, maybe let me back up. Whenever the turns ratio is larger than 1, which means we have a step-up transformer, this means the current on the primary side is going to be larger than the current on the secondary side. So while we have a step-up transformer, it's true that it will increase the voltage, but look at the cost of that. The secondary current is going to be less. So yes, we've increased the voltage on the secondary side, but the cost of that was that we have lowered the current on the secondary side. So the point is, a transformer is not magically making energy out of nowhere in increasing the voltage. Actually, it's just trading, it's an interplay between voltage and current. That's all it is. The same goes with a step-down transformer. Whenever the turns ratio is less than 1, notice whenever this guy here is less than 1, this means the primary current is going to be less than the secondary, which means we would have more current on the secondary side than we do on the primary side. So a step-down transformer, while it reduces the voltage, look at what it does to the current. It increases it. The current on the secondary is larger than that of the primary when you're using a step-down transformer. Actually, this is very important. The reason why that is important is, consider this circuit, this lower part of the circuit. I'm going to try to box it here. This lower part of the circuit. This lower part is what we call the filament circuit. It's the part where you have the cathode, which emits electrons from this side to that side. On this filament, we don't want a lot of voltage. Actually, we want a lot of current, because this is where we boil off electrons. So the more current, the better. We don't need a lot of voltage. However, on this side of the circuit, this is the side that we use to apply the kVp. On this side, we need a lot of voltage, but not a lot of current. So this is where we use a step-up transformer. So the step-up transformer will increase the voltage, but it will decrease the current. And this step-down transformer, it will decrease the voltage and increase the current. So this is why transformers are actually very important in the context of X-ray tubes. Of course, we also have a autotransformer. An autotransformer allows us to include or exclude as many windings as we'd like, depending on the kind of study or exposure we would like to carry out. So this is how transformers work. They are nothing more than playing around, or maybe I shouldn't say playing, but I should say they are interchanging the intensity of the voltage to that of the current. I will stop here. See you in the next video.